So while earlier I was running this, I was not really printing a summary. And there are two ways of doing the summary over here. So there is one this module called Torch Info. And if you look at Torch Info, there was a Torch summary earlier, which they've, I think, depreciated. And formerly, Torch summary is what they're saying. And yeah, so Torch Info provides information complementary to what is provided by printing of the model. Yeah, just print your model. So that print your model is over here. So this one. Yeah. And then there is one vanilla summary of the model wherein you don't give any input size and batch size. So I just call this test model batch size. We can just call it batch size. It doesn't really matter. These are the channels and these are the initial shapes. And how are these different? So we'll just come to that. First, I'll just go through various other things over here. So this we've just seen earlier. So the train model. So how is this working? And then the current loss, the current accuracy part of it. Uh, the optimizer step and loss being sent backwards, the backward propagation of loss. Uh, these are complementary to each other, and the optimizer step has got to do with the optimizer reducing your learning rate and then impacting the loss. So once the learning rate reduces, the loss reduces. So that is what we've seen over here. One second, I'll just so I'm printing within the test part of it. I'm printing the current loss and the current accuracy. So this we can see very clearly over here. So the current loss, I get about 200 printouts. So initially it starts at 28.44 and the current accuracy is 40 is what I'm presuming. Right, so it prints it in this particular manner. And if I were to go to the last value, the current loss is 7174 and the accuracy is gone to 7597. So while this would be read as 75% and this would be read as 71% over here, uh, the calculation of this is given as total accuracy and total loss. So which is current loss divided by length of data loader dot dataset. So my data loader dot dataset, if I'm not wrong, is 512, right? And total accuracy and total loss. This is what the formula is, and this is how it's getting printed. Test loss, is it? Yeah, this is the one. Uh, but then how is this related to the current loss? If this were to be, I don't know. I thought 512 was my value for this length of. So maybe I'll print this. I need to print this, and I'll probably then run this again. Right. So that is what I'll do, and let's call this 6. We already ran 5 of them. Mm, so will this be, yeah, data loader dataset. Okay, so while this one is still running, I'll go back to the earlier log and go back and walk through the code. So this we'll see. So if this result is okay and this is how it's calculated, which obviously it is, but just want to look at the numbers. Uh, Again, go back up. All of this I have already covered, and so yeah. So the zero grad, this we are done with. So we are basically making those gradients zero, and the reason we are doing that is that we don't want the earlier gradients to get added to this run. And then model inputs we are passing to this model. And okay, then again set grad enabled. This is again, it's a context manager. So the number of context managers that are being used to make the gradients uh, non-computable, so not to compute gradients. There are different context managers which are being used. This is one of them. So also, mm, one second. Yeah, so within the train, this context manager would be true, uh, right? So over here it is true, and within the eval or within the test, it will be false. uh, this can be used for conditionally enabling gradients, is what they mention over here in their documentation. So we don't want that in test, we want it in train. So yes, over here it remains true. And then torch max, out of the outputs, whatever is the max value is coming out as predictions. And the loss function, we've taken it as cross entropy over here, and the outputs and the labels. And in certain cases, in place of this labels, we'll have targets dictionary which is there. So that will be, and then um, optimizes step and loss backward. These both are complementary to each other. They are being used together in most of the cases. Mm, then current loss and current accuracy, we'll just see, we are printing that in the logs. So as to how that is increasing, we should also graph it actually. In a couple of other things that I had done earlier, it was getting graphed. And then the total loss and total accuracy, again calculation, we need to have a look at this. And this I've already covered earlier as to why we are using model eval and how is eval different from model train. Mm, okay, and so this is iterating over the data loader. This is the same as earlier, moving the inputs and the labels to device CUDA, the GPU. Then with torch dot set grad, this we've already seen why it is set as false. Uh, okay, then type outputs and type. So that's a tensor, and that outputs dot shape. That is something we should look at. And we should now look at our log 6. So, so yeah, this is what I thought. This figure of 10k uh, data loader dot datasets. Okay, so this I had not considered earlier. So 512 is something which I was getting earlier. I thought that was the number. Uh, but this is different. So obviously, these have become percentages, and these are the numbers. These are the actual numbers which have been achieved in the end. Okay, so this makes more sense now that we have this number out. Uh, so the outputs are a torch tensor, and this is the shape, and this is a continuous shape. It's always the same, and then it's not changing the output shape. And again, 200 printouts of that. So what obviously is changing is the labels tensor. So while you are passing in those images, that image label is changing definitely, because I don't I think this is shuffled in some manner. We will see multiple similar labels over there. So that is one. Okay. Now to look at the differences in these summaries. So this is one summary. Uh, this is the one which is coming out from when we are passing in this input size, which is first our batch size, then our channels and our shape. So if we pass this in as the initial over here, then let's look at this batch norm 2D, right? So this batch normalization, two-dimensional input layer, why does it have 128 over here as the parameter, right? And if it has 128, then this thing changes later on to 256, right? And when this changes to 256, the what is this? The channels is what I'm presuming change from 128. Uh, yeah, right. So this is something which is not so apparent over here, but if we were to go down and we were to look at, again, this one is now the summary which is without the mm, without any kind of input params, and then there is a printout uh, of that model, which is again down here. This is just the print of the model, and over here again we will note that the I'm just looking at this one particular layer so that we can correlate and we can understand. 64 is the initial, and how to understand this. Hmm, here, so the num features, the EPS, the momentum, fine. So the number of features, the EPS, the momentum, the affine, and the track running. So it is not filter size, sorry, it is the number of features. I said filter size earlier, my mistake. Uh, so expected input of, so this is number of features, this is height, this is width of the image. So that 2828 which we saw earlier over here, right? So this is the number of channels or the number of features, because it's three channels. So I thought maybe, yeah, but no, maybe the number of features. And 2828 is the height and width, right? And the first would be the batch size. So I presume that when they say n over here, so this is obviously the batch size. And EPS is a value added to the denominator for numerical stability. Default is exponential minus 5, is it? So yeah. Okay, so this is the EPS, and then there is momentum, which is 0.1 over here, and the value used for the running mean and running variable computation can be set to none for cumulative moving average, simple average. Default is okay, so this is the default value. Because obviously, yeah, we've not defined this anywhere. I don't think so. Then the affine true and track running stats true. A boolean value that when set to true, this module has learnable affine parameters. So okay, this is true by default. And track running stats, a boolean value that when set to true tracks the running mean and variance, and when set to false, this module does not track such statistics. Okay, so and then we will see that this 64 will change to 128, and when it is changed to 128, the conv2d second value is changed to 128, right? And here the conv2d second value was 64, and there the kernel size is 33. Okay. And what if I were to change this and run it? Then maybe I get a different kernel size. I don't know. So yeah, some of this needs to be understood, and this is total parameters and all of this is quite similar. So let me I got one earlier. mm, or is it in 5? Yeah. So this I got somewhere on the net. So while these values are different, the input values are different, but I still get 128 over here and 128 and then 256. So yeah, the batch normalization two-dimensional layer which is there, uh, this has got some similarity. And these total params also, I think they total up to the same thing, right? That's what we saw in 6 right now. Uh, no, they don't. Yeah, but similar numbers. So this is again for a ResNet. I just got it from somewhere and I just put it here just to compare and to try and understand how this is different from what we are getting. So this is the way to look at the summary, right? And this is the torch info is the one which is printing that summary. And then going back to the code, okay, yeah, so that's about it, and we don't really have much happening here. So now this is the second one which I need to run, and once this is run, and of course run this for different epochs, and then actually test a couple of images and see how that is going. Besides that, okay.